This research presents a novel preconditioned method for solving space-fractional diffusion equations, building upon the ideal preconditioner in J. Pestana, 2019. The standard discretization of the equation yields a non-symmetric, multi-level Toeplitz system, which is transformed into a symmetric multi-level Hankel system through a simple symmetrization strategy. A symmetric positive definite multi-level Tau preconditioner is proposed for the symmetrized system, leveraging discrete sine transforms for efficient implementation. Theoretically, mesh-independent convergence is demonstrated when using the minimal residual method, with eigenvalues of the preconditioned matrix bounded within disjoint intervals containing plus or minus 1. This work addresses the growing interest in developing effective preconditioners for symmetrized Toeplitz systems. A numerical method is presented for solving a multi-dimensional space-fractional advection diffusion equation with a source term, using a backward Euler method for the temporal derivative and the shifted Grunwald scheme for the space-fractional derivatives. The resulting linear system is a non-symmetric multi-level Toeplitz matrix, expressed as a sum of Kronecker products of identity matrices and Toeplitz matrices. The generating function of the matrix is given by f alpha, theta, equals nu plus n array summation I equals 1 dv, plus g alpha I, theta I, plus v, g alpha I, theta I. To solve the system, the MINRES method is employed, and a novel preconditioner is sought to expedite convergence. The authors note that circulant and band Toeplitz preconditioners are not suitable for the matrix, due to its ill-conditioning and fractional order. The stage is set for the introduction of a new preconditioning technique to tackle the challenges posed by the multi-level Toeplitz matrix. The matrix is transformed into a symmetric multi-level Hankel system through premultiplication with the anti-identity matrix, enabling the use of the MINRES method. The proposed Tau preconditioner is theoretically demonstrated to achieve mesh-independent convergence, with eigenvalues of the preconditioned matrix bounded within disjoint intervals containing plus or minus 1. The authors address the challenges of preconditioning non-symmetric multi-level Toeplitz systems, particularly in the context of space-fractional diffusion equations. They highlight the limitations of the ideal preconditioner proposed in 31, which, despite facilitating fast MINRES convergence, is computationally expensive and lacks theoretical justification. The authors' primary contributions are twofold. Firstly, they prove that the ideal preconditioner can indeed lead to a MINRES convergence rate independent of the mesh size. Secondly, they propose a novel multi-level Tau preconditioner, denoted as PN, as an improved alternative to the ideal preconditioner. This preconditioner balances effectiveness with computational feasibility, offering a practical strategy for preconditioning fractional diffusion equations and achieving mesh-independent MINRES convergence. The authors define the Tau preconditioner Pn in equation 2.4, which involves the symmetric part of the multi-level Toeplitz coefficient matrix and the Tau matrix approximation. They utilize the diagonalization property of the Tau matrix, expressed in equation 2.2, to efficiently compute the product of Pn and a given vector in O, n log n, operations using discrete sine transforms. The eigenvalues of the preconditioned matrix Pn(1) enan, where enan is defined by equation 1.7, are proven to be contained in a disjoint interval enclosing plus or minus 1. This result guarantees theoretically mesh-independent convergence when MINRES is applied. The authors also demonstrate the effectiveness of their proposed preconditioner through numerical examples in section 5, supporting the theoretical results concerning the eigenvalues of the associated preconditioned matrices. Multi-level Toeplitz and Hankel matrices are defined and discussed, along with their properties. These include being Hermitian if the generating function is real-valued, and Hermitian positive definite if the generating function is real-valued and non-negative. The permutation matrix Yn can be used to symmetrize multi-level Toeplitz matrices, such that Yntn, F, is a symmetric multi-level Hankel matrix. The asymptotic spectral distribution of Yntn, F, is crucial for developing effective preconditioners, and has been established for the unilevel case and generalized to the multilevel case. Two useful lemmas are provided, including lemma 4.1, which states that for non-negative numbers xi and positive numbers zeta I, It holds that min 1 is less than or equal to I is less than or equal to m xi I, zeta I is less than or equal to sigma I equals 1 meter xi I, sigma I equals 1 meter, zeta I is less than or equal to max E is less than or equal to m xi I, zeta I. Lemma 4.2 provides the generating function of a matrix ETM equals C1L, alpha, m plus C2, L, alpha, m, t, which is given by f alpha, theta, equals 2 sin theta, 2, caret alpha, C1 plus C2, cos, alpha, 2, pi theta, plus theta I, C2 C1, sin, alpha, 2, pi theta, plus theta. Here is the combined summary of the 4 pages. The ideal preconditioner H, n, is defined as n plus an, 2, and lemma 4.3 establishes its symmetric positive definiteness, ensuring preconditioning effectiveness for the system en x equals ynb. Lemma 4.4 provides a bound on the eigenvalues of H, n, minus 1/2 en n, minus 1/2, which lie in minus 1 minus e, minus 1, union, 1, 1 plus e. Proposition 1 bounds the essential supremum of the ratio of the imaginary part to the real part of f alpha, theta, denoted as s up theta element of minus pi d im f alpha theta re f alpha theta. This bound is expressed as max 1 is less than or equal to I is less than or equal to d plus minus d plus d minus tan alpha I 2 pi. The analysis further develops the bound on the essential supremum of the ratio of the imaginary part to the real part of f alpha, theta, establishing it as v plus minus v plus v minus tan alpha I 2 pi. This bound is then used to derive the final result, which is presented as the maximum of this bound over all I. Proposition 2 establishes that the eigenvalues of H, n, minus 1 en lie in minus 1 plus e, minus 1, union, 1, 1 plus e, ensuring optimal convergence of the MINRES method. Specifically, the kth residual of R, k, satisfies parallel R, k, parallel 2, parallel R, 0, parallel 2 is less than or equal to 2, beta minus 1, beta plus 1, k, 2. The proposed practical preconditioner Pn is introduced, and lemma 4.5 guarantees its positive definiteness. Lemma 4.6 states that the eigenvalues of tau, h, l, alpha, m, minus 1 h, l, alpha, m, lie in 1/2, 3/2, for alpha element of 1, 2, and m greater than 0. Proposition 3 shows that Pn and H, n, are spectrally equivalent, with the eigenvalues of p minus 1 nanohenry, and lying in 1/2, 3/2. This result is established by combining lemma 4.6 with the Rayleigh quotient theorem, implying that the preconditioner Pn can effectively replace H, n, in the MINRES method, ensuring optimal convergence. The proposed preconditioner Pn for the system matrix En in a unidimensional fractional diffusion problem is shown to be effective through theorem 4.1, which states that the eigenvalues of Pn1 En lie in the intervals minus 3/2, 1 plus e, minus 1/2, union, 1/2, 3/2, 1 plus e, where e less than max 1 is less than or equal to I is less than or equal to d plus d minus d plus d minus tan alpha I 2 pi. This result is achieved by utilizing Ostrowski's theorem and propositions 1 and 3, providing bounds on the eigenvalues of Pn1/2 H, and Pn1/2 and H, and 1/2 en and 1/2, respectively. Consequently, the residuals generated by MINRES for the preconditioned system satisfy parallel R, k, parallel 2, parallel R, 0, parallel 2 is less than or equal to 2 omega, k, with omega equals square root 2 plus 3e, 4 plus 3e, element of 1/2, 1. Numerical experiments in Section 5 compare the performance of Pn against existing ideal Toeplitz preconditioners AR and AM from 31. The MINRES solver is used with the identity matrix, Pn, and multigrid approximations of AR and AM, denoted as minresult, Pn, Mg, AR, Mg, AM. The tests are conducted on a unidimensional fractional diffusion problem with zero initial condition, with parameters h and tau chosen to ensure a constant nu throughout the computations. The first test examines the performance of the preconditioners for different fractional derivative orders, alpha equals 1.1, alpha equals 1.3, alpha equals 1.5, and alpha equals 1.9. Table 1 shows that the iteration count for minres Pn remains stable across different values of alpha as the spatial grid is refined, requires less CPU time than MINRESMG, AR, and MINRESMG, AM, and demonstrates an improved preconditioning effect as alpha approaches 2, consistent with Theorem 4.1. Figures 16 display the eigenvalues of Pn1 Enan for various values of alpha and n, confirming the presence of a disjoint interval predicted by Theorem 4.1 and the improved preconditioning effect as alpha approaches 2. Table 2 examines the impact of diffusion coefficients d1 plus and d1 on the performance of the preconditioners, showing that the difference, d1 plus d1, affects the convergence, not the individual values themselves. The results indicate that the proposed minres Pn outperforms both MINRESMG, AM, and MINRESMG, AR, in terms of CPU times, while all preconditioners demonstrate optimal performance in terms of iteration count. However, the CPU time for minres Pn does not scale properly with n, potentially due to the limited size of n. The MINRES algorithm is evaluated for solving non-symmetric linear systems, focusing on its performance for different values of parameters alpha, d1, plus, and d1. Tables 1 and 2 present the results for example 5.1, showcasing the iteration numbers and CPU times for the MINRES algorithm with and without preconditioning. The eigenvalues of the matrix Enan are plotted in Figure 2, demonstrating the clustering of eigenvalues around the origin, indicating the effectiveness of the preconditioner. The results in Tables 1 and 2 demonstrate the efficiency and robustness of the MINRES algorithm with preconditioning, achieving significant reductions in iteration numbers and CPU times compared to the unpreconditioned case. The preconditioner Pn is shown to be effective in reducing the iteration numbers and CPU times, especially for larger values of the parameters. Further investigation of the eigenvalues of the matrix Enan with and without preconditioner Pn reveals the effectiveness of the preconditioner in clustering the eigenvalues, leading to improved convergence of the MINRES solver. Table 3 reports the iteration count and CPU time for the MINRES solver using various preconditioners, across different orders of fractional derivatives, alpha 1, alpha 2, and mesh sizes n equals n1 n2. The findings highlight that minres Pn achieves iteration counts that are independent of the mesh size, making it the most efficient method. The convergence of minres Pn is determined by the maximum of tan, alpha I, 2 pi, for I equals 1, 2, rather than each tan, alpha I, 2 pi, individually. As alpha 1 and alpha 2 approach 2, the convergence of minres Pn improves due to the corresponding reduction of the maximum towards 0. Figures 712 validate Theorem 4.1, demonstrating the improved effectiveness of preconditioning when both alpha 1 and alpha 2 are close to 2. The novel approach for solving space-fractional diffusion equations using a MINRES method based on multilevel Tau preconditioners is efficient and effective, achieving iteration counts that are independent of the mesh size. The MINRES method with preconditioner Pn is applied to example 5.2, yielding significant improvements in convergence rates and CPU times compared to the unpreconditioned MINRES method, as demonstrated in Table 3. The preconditioner clusters the eigenvalues of Enan, as shown in Figures 10-12, leading to faster convergence. This improvement implies that the preconditioned MINRES method's performance is independent of the mesh size. Numerical examples demonstrate the superiority of the proposed preconditioning strategy, achieving faster convergence and reduced CPU times. The proposed preconditioner is based on the absolute value function, f, and tau matrices. Future work will focus on developing a practical and effective preconditioner for symmetrized multi-level Toeplitz systems. Recent studies have extensively explored the properties and applications of Toeplitz matrices, including spectral analysis, computational properties, and preconditioning techniques. References 27 provide a comprehensive overview of these topics. Moreover, 57 introduce optimal circulant preconditioners, analyze preconditioning techniques, and present a unifying approach to abstract matrix algebra preconditioning, respectively. Later works, 824, have focused on the spectral analysis and structure-preserving preconditioners for fractional diffusion equations, multi-level symmetrized Toeplitz structures, and eigenvalue distribution of special 2x2 block matrix sequences. These studies have significantly advanced our understanding of Toeplitz matrices and their applications. The development of efficient preconditioning techniques for large-scale linear systems, particularly those arising from ill-conditioned Toeplitz matrices, is crucial. By leveraging spectral properties and structure, researchers can design effective preconditioners that improve convergence and accuracy. The proposed preconditioned MINRES method demonstrates this potential, offering improvements in both theoretical and numerical aspects. Recent studies on preconditioners for non-symmetric and time-dependent partial differential equations, PDEs, and their applications to fractional diffusion equations have led to the development of efficient iterative methods. Finite difference approximations for two-sided space-fractional PDEs were proposed by Mark M. Meerschaert and Charles Tadgeron, while Eleanor MacDonald et al. Developed preconditioning methods for non-symmetric and time-dependent PDEs using domain decomposition techniques. Iterative methods for Toeplitz systems were presented by Michael K. Ng, and multigrid and fast numerical contour integral methods for fractional diffusion equations were introduced by Hong Kui Pang and Haiwei Sun. Preconditioners for symmetrized Toeplitz and multi-level Toeplitz matrices were developed by Jennifer Pestana, as well as a preconditioned MINRES method for non-symmetric Toeplitz matrices. Stefano Serra Capizzano proposed Toeplitz preconditioners constructed from linear approximation processes, and Gilbert Strang proposed a method for Toeplitz matrix calculations. Andrew J. Wathen provided a comprehensive overview of preconditioning techniques in Acta Numerica, 2015. These references collectively highlight the importance of preconditioning in solving large-scale linear systems arising from PDEs and demonstrate the need for efficient and robust preconditioning techniques. The analysis of these methods highlights the importance of considering the structure of the matrices and the properties of the underlying PDEs when designing efficient preconditioners. The methods and results presented provide a foundation for the development of advanced preconditioning techniques for fractional diffusion equations and other complex PDEs. The preconditioning techniques discussed in these references include domain decomposition, multigrid, and Toeplitz preconditioners, which are designed to exploit the structure of the matrices and the properties of the underlying PDEs. These techniques have been shown to be effective in reducing the computational cost and improving the accuracy of iterative methods for solving large-scale linear systems arising from PDEs. Note: please provide the content of pages 2728 so I can complete the combined summary of the 4 pages.